Hello, and welcome to Linear Algebra. This is lecture 21, and our topic is similar matrices. So last time, we talked about change of basis. This time, we want to talk about matrices that represent the same linear map after a change of basis. Okay, so let me remind you. If T is a linear map from a vector space to itself, and you have two different bases of that vector space, then the matrix associated to T with respect to the basis B prime is related to the matrix associated to T with respect to the basis B by multiplication by two change of basis matrices. This one would start with the basis B prime and end with the basis B, and this one would start with the basis B and end with the basis B prime, right? Or if we go ahead and say that S is equal to the change of basis matrix on the left, then this says that T with respect to the basis B prime is equal to S times the matrix associated to T with respect to the basis B times S inverse. Okay? So if I have a linear map and I express it in two different bases, the matrices I get are related to each other. They're related by this formula. So let's call matrices related in this way similar. So we'll say the two matrices size n by n are similar if there is an invertible matrix call it S, such that B is equal to SA S inverse. Okay, and then right away we have a theorem saying that the way we came up with similar matrices is the only way you can come up with similar matrices. That is, two matrices are similar if and only if they represent the same linear map in different bases. Okay, so it's an if and only if, so we need to prove both directions, but we've already seen we already know that the matrix associated to T with respect to the basis V and the matrix associated to T with respect to the basis B prime are similar. So we just need to prove the other direction. So assume A and B are similar matrices with B equal to SA S inverse. Okay, then let's claim that S is a change of basis matrix. And hence, A and B represent the same linear map, right? So if I show that every change of basis, every invertible matrix is a change of basis matrix, then we're done, because then this is exactly this. Okay, so let's prove that. Well, indeed, let's say that the columns of S are sigma 1 through sigma n. And then let's take A to be the list of these columns. A is a basis. And S is exactly the change of basis matrix, starting with A, ending with the standard basis. Right? So how do we know that this is a basis? Well, we already saw this, right? A matrix is invertible if and only if its reduced row echelon form is the identity matrix, which is equivalent to saying that the columns are a basis of Fn. And then we saw last time that it's really easy to write the change of basis matrix when you want to end up with the standard basis, because what you're given are exactly the basis elements written with respect to the standard basis, right? So S is this change of basis matrix. And so we're done. Okay, excellent. So now we can take concepts about linear maps and write them as concepts about matrices. So for example, last time we saw that a linear map is diagonalizable if there is an eigenbasis for it. But the definition is that a linear map is diagonalizable if there is a basis in which that linear map is given by multiplication by a diagonal matrix. So let's define a matrix is diagonalizable if it is similar to a diagonal matrix. Equivalently, if it represents a diagonalizable map. Okay, so as I mentioned a second ago, a linear map is diagonalizable precisely when it has an eigenbasis, when there is a basis of the vector space consisting entirely of eigenvectors. Okay, so of course something similar, well, the same is true for a matrix, but let's think about what this looks like in terms of similarity. So if you give me an n by n matrix, and it turns out that it's similar to a diagonal matrix, so let's write that as A is SD S inverse with D a diagonal matrix, entries lambda 1 through lambda n on the diagonal, then, well, multiplying by S on both sides, on the right, it's true that S times D is equal to A times S. So if we do as we did a second ago and write S as the matrix whose columns are sigma 1 through sigma n, then, okay, what does this say? Well, A times S is the matrix whose columns are A times sigma 1 through A times sigma n. On the other hand, S times D, well, D is a diagonal matrix, so it's really easy to do S times D. I'm going to get lambda 1 sigma 1 all the way to lambda n sigma n. Right. If you like, just do the same thing as we did here. For s times d, you're going to get the first column is going to be s times the first column of d, and that gives you lambda 1 sigma 1, and so on. These are vectors, bars. Okay, but if we're saying that this matrix is the same as this matrix, then in particular, each column is the same as the corresponding column. So we're saying that A times sigma j is equal to lambda j sigma j for every j. And since sigma j is not a zero vector, right, because as it's an invertible matrix, this says that the columns of S make up an eigenbasis of A. On the other hand, if for some A, we have an eigenbasis, right? A basis consisting entirely of eigenvectors, sigma 1 through sigma n, and we put S as the matrix whose columns are the elements of that basis, then S inverse AS by the same computation is the diagonal matrix whose diagonal elements are the eigenvalues corresponding to these eigenvectors. So we want to have a special name for properties of a matrix that actually are properties of linear maps associated to that matrix, right? So we're going to call those things invariants. A property of a matrix is called invariant if it is preserved by similarity. Right. So another way of saying that is it's a property of a matrix that doesn't change when you change basis, when you look at things using a different basis. So from the theorem, invariant properties of a matrix are properties of the associated linear map. For example, similar matrices have the same eigenvalues. Right? Not the same eigenvectors, but the same eigenvalues. Right? Indeed, these are just the eigenvalues of the associated linear map. Right? Linear maps have eigenvalues, and every matrix associated to a linear map, doesn't matter what bases, has the same eigenvalues as the linear map. You can also see this directly. Assume that B is equal to SA S inverse, and V is a non-zero vector, eigenvector for B. So if V times V is equal to lambda V, then SA S inverse of V is equal to lambda V. If I multiply both sides by S inverse, I get that A S inverse of V is equal to lambda S inverse of V. And since S inverse of V is also not zero, right? Because S is an invertible map, S inverse is not going to take a non-zero vector to 0. This shows S inverse of V is an eigenvector of A with eigenvalue lambda. So notice that the eigenvalue is the same, the eigenvector is different. Okay, great. So that example shouldn't have been surprising since we've been talking about eigenvalues and diagonalizability. Here's another example. Similar matrices have the same rank and nullity. Okay, so you might think that also not surprising, because after all, there's a linear map, and the linear map has a rank and a nullity. That's true, but we still need to prove this lemma. It says that if you have a linear map between two vector spaces with VW finite dimensional, and you pick bases, then the rank of T is the same as the rank of the matrix associated to T with these bases, and the nullity of T is equal to the nullity of the matrix associated to T with respect to these bases. Okay. So let's prove this lemma, and then it will be clear that similar matrices have the same rank and nullity, because by the lemma, those will be the same as the rank and nullity of the associated linear map. Okay, so if you give me a vector in the null space of T, then I know that 0 is exactly that, represented with the basis VW, and the action of the matrix is such that this is given by this matrix times this vector, right? So if you ended up with 0, then that means that this vector is in the null space of this matrix. Right, so the vector representation, the coordinates representation with respect to this basis, is in the null space of this matrix, and vice versa. right? If you have a vector in the kernel of this matrix, then by this equality, you know that the vector is in the kernel of T, of the linear map. That's enough to see that the nullity of T is equal to the nullity of the matrix. And then from the rank nullity theorem, if the nullities coincide, the ranks also coincide. Okay, so perfect. That gives us a second and third examples of properties shared by similar matrices, right? Perhaps most interesting is to turn this around. So we can also define properties of T using matrices associated to it as long as the property is invariant, right? So if you give me a matrix representing T, then some properties of this matrix, like what is the first entry, are not going to be invariant. So they don't actually reflect properties of T, right? But if I find some property that is the same for all similar matrices, then it's actually a property of T. Perhaps it's simpler to express in terms of matrices. Here's an example. Let's define the trace of an n by n matrix to be the sum of the elements on the diagonal. Okay, so what we're going to show is that this trace is an invariant of A, and hence it's a property of linear maps. Okay, so to do that, we're actually going to show something a little stronger than we need, but this very cool property of the trace. If you have two matrices, so the trace is only defined for square matrices. But let's say that I have matrices whose sizes are such that A times B is a square matrix, and B times A is also a square matrix. So possibly different size square matrices, but they're both square. That's enough for the trace to coincide. So the trace of AB is equal to the trace of BA. As long as AB and BA are both square matrices, it doesn't matter what size A and B are. Okay, and the proof is really quick. So the trace of A times B is the same as, well, it's the sum of the elements on the diagonal. So A times B is an m by n matrix, so I add m things. And it's just the I entry of the matrix A times B. Now we can write that out. So this would be the sum I goes from 1 to m of the sum j goes from 1 to n of A, I, j, B, j, I. And then we just change the order of the sum. So now we have j goes from 1 to n of the sum I goes from 1 to m of the same thing, A, I, j, B, j, I. But now we recognize that as the sum j goes from 1 to n of the jj entry of b times a, and that is the trace of BA. Okay, so you see it's a very simple identity when you get it down to these iterated sums. But of course, an immediate corollary of this is that if A and B are similar matrices, then the trace of A is equal to the trace of B. Right, and the proof, of course, is easy. So if B is equal to SA S inverse, then the trace of B is equal to the trace of SA S inverse, which I'm going to view as S times A S inverse. And then by the property of the trace from the proposition, I can change the order of the product without changing the trace. But now A times S inverse times S is just A. Okay, so in particular, right, as we said to motivate this, if T is a linear map from a vector space to itself, and BB prime are bases of V, then the trace of the matrix associated to T with respect to the basis B is the same as the trace of the matrix associated to T with respect to the basis B prime. So we define the trace of T to be this common value. Okay, let's work out an example where we can see this with specific entries. So let's let R theta be, as usual, the map from R2 to R2 that rotates counterclockwise by an angle of theta radians. Okay, then the matrix associated to R theta with respect to the standard basis, right? So E1, E2 is, okay, R theta square bracket sub E. So as we've seen, this is cosine theta sine theta minus sine theta cosine theta. So the trace of this matrix representation is 2 times cosine theta. Okay, let's pick a different basis. If we used instead the basis A, so let's say the basis has first vector 1, 1, and second vector 0, 1, then since, okay, so I want to find the matrix associated to R theta with respect to this basis, right? So remember, one way to find this is one column at a time. To find the first column, I'll take the first basis vector, I will hit it with R theta, and then I'll express the result with respect to this basis. Right, so r theta of the vector 1, 1. Well, since I have this matrix right here, it's very easy to compute this. See that I get cosine theta minus sine theta, and then the second entry is sine theta plus cosine theta. And I can write this as cosine theta minus sine theta times the vector 1, 1 plus 2 sine theta times the vector 0, 1. And then r theta of the vector 0, 1 is, well, minus sine theta cosine theta, right? It's the second column of this matrix. And I can express this in terms of the basis A as minus sine theta 1, 1 plus cosine theta plus sine theta 0, 1. So putting those together, we see that the matrix associated to r theta with respect to the basis A has entries, well, here, these coefficients are going to be the first column, and these coefficients are going to make up the second column. So I get cosine theta minus sine theta, and then 2 sine theta, and then minus sine theta, and then cosine theta plus sine theta. Right, and notice that the trace of this matrix is equal to, well, cosine theta minus sine theta plus cosine theta plus sine theta. So 2 times cosine theta, right? As it had to be because we had already computed this trace with the standard basis. So either computation shows that the trace of this linear map is 2 times cosine theta. Okay, and we'll stop there and pick it up next time.